Let's now extend this concept of resonance to polyatomic ions, and we'll find that in fact many of these polyatomic oxyanions really do exhibit a lot of resonance structures, and it's very important in really understanding their structure and the charge distribution on them. Our learning goals here are once again to look at elements that exhibit a expanded valence shell and what the implications are for that, and also the importance of resonance structures in these polyatomic ions. Let's start by looking at the sulfate ion. Okay, that's SO4 with a 2- charge, so when we count up the electrons we should come up with 32 valence electrons. The least electronegative element is the central atom in this case, and so since sulfur and oxygen both form 2 bonds, we can't base it on the one that forms more bonds. So in this case we take the less electronegative element, which is sulfur. This connectivity will use 8 of the electrons, which leaves 24, and this results in the bond connectivity diagram that looks like this. You note that sulfur has 4 bonds in this structure, not 2. So it has more bonds, but it has, after we've added the remaining 24 electrons, we've used up all the electrons, so there are no non-bonding electrons left to put onto the sulfur. All of these atoms satisfy the octet rule, so this would be a happy circumstance based on the octet rule. And if we calculate the formal charges, we would find that sulfur normally has 6 valence electrons. It only has 4, 1 for each bond, so now it has a +2 charge. That's interesting. Each of these oxygens, this represents that same common circumstance where oxygen has 1 bond and 6 non-bonding electrons, so it has a formal charge of -1. Now notice that the total charge on this is we've got 4 -1s and 1 + 2, so the total charge is going to be 2 - 4 or -2. So we might draw the sulfate ion with brackets around it and a 2- to indicate the total charge on it. All right, now this would be a reasonably good, perfectly legitimate Lewis structure with formal charges noted. If we were to do the same exercise for phosphorus, we would end up with, for the phosphate ion, we would end up with a structure similarly, except that now there's only a +1 charge on the phosphorus and an overall -3 charge for the ion. So this is sulfate and phosphate using all the rules that we've developed up until now. Okay, remember though that sulfur and phosphorus are both in the 3rd row, so they can have an expanded valence shell. And in fact, this allows them to relieve some of that formal charge by forming multiple bonds. All right, so those central atoms can accommodate more electrons. We can form double bonds. So what that looks like in the sulfate ion is we might form extra double bonds at the top and the bottom. And this would result in a structure that looks like this, where now we only have 2 atoms with formal charge, and all the others are with 0 formal charge, and all the oxygens obey the octet rule, but sulfur has an expanded valence shell. Okay, similarly in phosphorus, we could form 1 double bond. I've done this on the top, and this now creates a situation where the phosphorus and 1 of the oxygens have no formal charge, and 3 of the oxygens remain with a -1 formal charge to give the total ion a -3 charge. So in both cases, there is a possibility using the expanded valence shell of these elements to form multiple bonds and reduce the number of atoms that have a formal charge. But now sulfur has 12 and phosphorus has 10 valence electrons, so clearly they have expanded their valence shell quite a bit. Okay, all of the sulfur oxygen bonds in the sulfate ion are found to be equivalent. So that means that we can form various resonance structures, just as we did for ozone and in the previous video. In the case of sulfate, there's a total of 6 equivalent resonance structures. That's the number of ways that one can distribute 2 double bonds among 4 equivalent bonds. All right, so it would be an interesting exercise to give on a test, but I would never do that to you. So just appreciate the fact that there can be many resonance structures when we have a complex polyatomic ion like sulfate. What is the relative importance of these structures? Well, the ones that count the most, and I said that the first structure was a legitimate structure, but the ones that count the most have several qualities that we would look for. One, they would have fewer atoms with formal charge. That's why we engage in creating the expanded valence shell versions of these without so many formal charges. we would want to have negative charges on the most electronegative atoms. You notice in the final case for sulfate and phosphate, all the negative charges were on oxygen and none on phosphorus or sulfur, because oxygen is more electronegative. They would have opposite charges close to each other in the structure. Now in this case we eliminated the opposite charge by creating the extra multiple bonds, because phosphorus and sulfur could expand their valence shell. So in this case, in phosphorus, we would have these two possibilities, one where there's all single bonds, one where there's a double bond. And it's the bottom structure that will contribute more to the average structure of the phosphate ion, simply because it has fewer atoms with formal charge. That would be the criterion we would use. So, when you're looking at these things and you're saying, well, which one really matters more, it's the bottom one that will matter more. But certainly there are instances where we would see evidence of a slight positive charge on the phosphorus ion that would lend some weight to the top one as well. Okay, the resonance structures result in the following average structures for these two ions. Okay, for sulfur, we would form 4 partial bonds, partial double bonds to the oxygens. Each oxygen atom would have a -1/2 charge on average. Okay, what we want is we want all of those equivalent atoms to add up to the total charge on the ion. Since the total charge is -2 and there are 4 of them, each of them must have a -1/2. Similarly, for phosphate, we would draw equivalent structures that look like partial double bonds between phosphorus and each of the oxygens. But in this case, each oxygen has an averaged negative charge of -3/4. There's 4 of them. The total charge on the ion is -3, so each of them must carry on average about a -3/4 charge. I hope this has made some sense, and that you can begin to utilize resonance structures in understanding what these polyatomic ions look like. The key to remember is that Lewis structures are a device that helps us understand something about bonding, but it has limitations, and in particular when electrons get delocalized across an entire structure, the Lewis structure picture is a little bit too restrictive in terms of what it predicts.